So in the second part of 7.2, we're going to look at how to write functions as a piecewise function. And this is probably the most important thing that you can take away from 7.2, because the piecewise function will be used in section 7.3 to solve equations. So you've seen in all of the graphing that we did that a function is made up of two or more pieces. The pieces that it's made up of is the positive piece, which we saw stayed the same on all of our graphs, and the negative piece, which we saw on all of the graphs, was reflected in the x-axis. So we have to look at each one of those pieces, because when we take the absolute value, the result stays the same, but we have to look at the domain that resulted in those positive pieces. So the absolute value of x is a piecewise function, since the absolute value of a positive x is x, and the absolute value of a negative x is also positive x. So let's look at how to write it as a piecewise function. So here we have the graph f of x equals x. So it's just the identity function that passes straight through the x-axis. So you can see that we first of all have a positive piece, and that positive piece happens when x is greater than or equal to 0. But we also have a negative piece, and when I take the absolute value of that negative piece, it will also become positive. So I have a negative piece when x is less than 0. So you can see I have two pieces that I need to consider. So if I look at the graph of absolute value of x, you can see where these two pieces come into play. So that positive piece is this piece here that stays the same. So when x was greater than or equal to 0, the graph absolute value of x was just the graph y equals to x. So it stayed the same. But when we had x less than 0, this piece here, this negative piece, is reflected in the x-axis. So the graph absolute value of x becomes the graph of y equal to x reflected in the x-axis. So here's my two pieces. I have the positive piece where f of x equals x when x is greater than or equal to 0. But then I have that negative piece where this graph here, y equal to x, is reflected in the x-axis to become y equals negative x. So that's why it's negative x when x is less than 0. So those are the two pieces of the piecewise function y equals the absolute value of x. So let's take that into an example, the absolute value of 2x minus 3. So you can see here I've graphed the line y equals 2x minus 3, and let's examine it. First of all, it has a positive piece, and the positive piece occurs when x is greater than or equal to 2.5. So when x is greater than or equal to 2.5, the graph of the absolute value is just the graph 2x minus 3. So that means that the positive piece is just 2x minus 3 when x greater than or equal to positive 2.5. The negative piece, however, occurs when x is less than 2.5. So you can see when x is less than 2.5, the absolute value function is actually the graph of 2x minus 3 reflected in the x-axis. So it's going to become the graph negative 2x plus 3. So you can see here in my graph of my absolute value, you can see here the positive piece, and you can see the negative piece is reflected in the x-axis. So this negative piece becomes negative 2x plus 3 when x is less than 2.5. So this here makes up the piecewise function, the positive piece and the negative piece, and the domain in which both occur. So you can see I do have the domain and range that I need to list for this function. So as before, the domain is just x is an element to the reals, and the range y greater than or equal to 0. So now I want you guys to try one on your own. I want you to write this absolute value of 3x plus 1 as a piecewise function. So pause the video now, do the question, and then press play to compare your answer to mine. Okay, so taking the graph of 3x plus 1, where the x-intercept is at negative 1/3, you can look at, first of all, the positive piece. So this graph is positive when x is greater than or equal to negative 1/3. So what that means is when x is greater than or equal to negative 1/3, the absolute value function is just the graph 3x plus 1. So when I come down to my piecewise function, the positive piece is just 3x plus 1 when x is greater than or equal to negative 1/3. The negative piece occurs when x is less than negative a third. Notice it's not equal to. When it's equal to, that means it's at 0. That's positive. So the negative piece won't include equal. It's just less than negative a third. So when it's less than negative a third, that graph, the absolute value function, is going to be the graph of 3x plus 1 reflected in the x-axis, because remember, this negative piece is going to come up. So when it's reflected, it's going to have the equation negative 3x minus 1, and that becomes our negative piece. Negative 3x minus 1 when x is less than 2.5. Nope, that's wrong. When x is less than negative 1/3. So a little typo there. Let's change that to negative 1/3. Okay, so we have the positive and the negative piece. So that's how to do it with linear functions. I want to now look at how to do that with quadratic functions. So you can see in this example here, we're going to do the piecewise function of negative x squared plus 2x plus 3. So the process is exactly the same. The only thing that's different is the graph. So you can see I have my parabola, I have the x-intercepts labeled. So let's firstly look at the positive piece. So the positive piece above the x-axis is when x is in between negative 1 and positive 3. So when x is in between negative 1 and positive 3, the graph will just be negative x squared plus 2x plus 3. It'll be just the regular parabola that opens down. Let's look at the negative pieces. So there are two parts of the graph where the graph is negative. One when x is less than negative 3, and the other when x is greater than 3. Now these pieces, remember, are going to be reflected upwards. So when x is less than negative 1 and greater than 3, the absolute value function will be this original parabola reflected in the x-axis. So it will have an equation of x squared minus 2x minus 3. So notice everything has been reflected. So here becomes my positive piece. X squared minus 2x minus 3 when x is less than negative 1 or greater than 3. So if we actually look at the graph of the absolute value, you can see there's my pieces that have been reflected. Okay, and it fits with the piecewise function. Again, listing out the domain and range. Domain is that x is an element of the reals, and range y greater than or equal to 0. So the only thing that's changed here is just the graph. So I have one for you guys to try on your own. So at this point, pause the video, do your question, and come back, press play, and see how your answer compares to mine. Okay, so for this graph here, we'll identify first of all the positive pieces. So the positive piece there happens when x is less than negative 1 or greater than 6. So the positive piece is going to be, the absolute value will be just the graph of x squared minus 5x minus 6. So that means the positive piece there occurs when x is less than, and let's add on equal to negative 1, or y is greater than or equal to 6. Now let's look at the negative piece. So the negative piece below the x-axis happens when x is in between negative 1 and 6. So what that means is that the absolute value function will be the graph of x squared minus 5x minus 6 reflected in the x-axis. So it becomes negative x squared plus 5x plus 6. So you can see here my negative piece is that between negative 1 and positive 6. So again, the only difference between this and the linear is the graph. So if you need to go back and watch those examples again, please do so. I want to make sure that you guys are completely comfortable with piecewise functions, because as I said, we do need those for section 7.3. So you guys can go and do the practice questions. Remember, absolute values won't put up with any negativity, because when you take the absolute value of a negative, it becomes a positive. Hope that helped. And we'll talk about section 7.3, solving absolute value functions, tomorrow.